Greetings, viewers. My name is Adenata Supriadi, and today I'll be presenting about Praktikum Metalurgi, especially in manufacturing properties of material. So, most of the reference of the material here is taken from this book, Manufacturing, Engineering, and Technology, by Seropi Kalpakjan and Stephen R. Schmidt. Contents. So what we'll be discussing today is, first we got tension, hardness, impact, and finally metallography. Okay, so tension. So through a tension test, what mechanical properties of a material can we obtain? First, we can obtain its strength, ductility, toughness, its elastic modulus, and its strain hardening capabilities. Okay, so to do a test, we'll need a specimen. So what does this specimen look like? This is what a typical tension test specimen look like. We got its original gauge length, signified by LO, and then we've got its cross-sectional area, signified by AO. So its cross-sectional area is right about here, or anywhere to be exact. The point is, all our measurements have to be within this so-called shoulder. And then through a tension test, we can make what's called a stress-strain curve. So what is a stress-strain curve? Let me explain. So first, here we have our specimen with its original gauge length, and then we apply load to each ends, and what that does is it pulls apart this specimen and makes it longer and thinner, actually. So it doesn't only elongates it, it makes its cross-sectional area, or AO, thinner, smaller. Here we have LE. So in this point, up until this point, the specimen elongates elastically. So what that means is, if we were to remove all load from the specimen would snap back to its original length, both in LO and its original cross-sectional area. However, if we were to, say, apply load past this point, all the way up here, all the way anywhere to be actually, the specimen would deform plastically, and what that means is it would not snap back to its original length, hence the plastic. And here, at this point, we have what's called a UTS, or ultimate tensile strength. Okay, so at this point, the specimen have elongated or expanded to its maximum length, to its maximum capabilities, hence the ultimate. So if we were to pull it past this point, a neck would start to appear. So once this neck appears, all expansion, all elongation would be centered around this neck, and that is where the fracture would also happen. AF is the cross-sectional area of the fracture. Okay, now we have engineering stress and strain. We have what's called a true stress and true strain, but I'll explain this first. So we have engineering stress. So we denote engineering stress by dividing the load applied to the material, to the specimen, divided by the material's original cross-sectional area. Quite self-explanatory. And then we have engineering strain. So what is engineering strain? It is defined as the difference in length, or elongation, divided by its original gauge length. So here, what is this graph? This graph is a graph that we will obtain straight out of the testing the specimen. So this is not the same as our previous graph, where this graph is a stress and strain graph. This graph is a load and elongation graph. So I don't think you can see it, but right down there it says delta L, signifying elongation. So what we're gonna do with this graph is we're going to convert the data that we obtain here using these formulas to obtain a engineering stress and strain curve. We'll dive deeper into that in a bit, but first let me explain about Young's modulus, or the modulus of elasticity. We get this from dividing stress with strength. Next we have ductility. So what is ductility? Ductility is the extent of plastic deformation that the material undergoes before fracture. So in a nutshell, ductility is how much we can pull a material apart before it fractures or tears apart. Common measures of ductility. First is total elongation. We obtain total elongation by the specimen's final length minus its original length divided by its original length and multiplied by 100. Similar to total elongation, here is the material's original cross-sectional area minus its final cross-sectional area. True stress and true strain. Okay, as I have previously mentioned, we have what's called a true stress and true strain. So what is true stress and true strain? In a nutshell, let's take this for example. The ratio of the load P to the actual cross-sectional area. Here we have actual cross-sectional area, which means that instead of using its original length, what we use here is its actual area, cross-sectional area. So as we pull apart this specimen, the cross-sectional area would get smaller and smaller over time. So the value for A depends on that actual cross-sectional area. Same goes for true strain. Then we have construction of stress-strain curves. Okay, as I have previously explained, straight out of the test, we have what's called a load elongation curve. Tension test of stainless steel. So this is straight out of testing. We get load on the y-axis and extension on the x-axis. And then we can convert this into the engineering stress-strain curve and then to the true stress-strain curve. This is a weird phenomena, but I'll explain that in further detail in the next slide. Okay, so we have correction. What is happening here? So here's the true stress-strain equation. Correction to the curve reflecting the fact that the specimen's neck region is subjected to three-dimensional tensile stresses. This gives higher stress values than the actual true stress. To compensate, the curve must be corrected downward. The true stress, true strain curve in figure 2.5c can be represented by the equation. So here is the equation that represents the true stress, true strain curve. Okay, so what is going on here? We have what's called a strain hardening phenomena, where if you were to pull apart a specimen, this specimen, what happens is the crystals and the atoms in the material will start to they get pulled apart, and that actually makes the material harder and stronger and more resistant to being pulled apart, hence this line. So we are correcting it by curving it downward. Okay, next we have hardness. So what is hardness? What can we get from a hardness test? So indications given from a hardness test is a material's strength, resistance to scratching, and resistance to wear. Okay, what is hardness? Hardness is defined as resistance to permanent indentation. Okay, the reference material gave us 4 examples of a hardness test device. First we got micro Vickers hardness tester, and then we got the Rockwell hardness tester, and then we got the durometer, and then last but not least we got the leap tester. So here are the 4 examples given in the reference material, and I'll explain them one by one. First we got the Brinell test. Pressing a steel or tungsten carbide ball 10 mm in diameter against a surface with a load of 500, 1500, and 3000 kilograms. Okay, from that we get what's called a Brinell hardness number, signified by HB, hardness Brinell. Ratio of the load P to the curved surface area of the indentation. So the Brinell hardness number is acquired by this formula, 2P. P is the load applied, 500, 1500, or 3000, divided by this. D, big D, is the original diameter of the indenter, or in this case 10 mm, and small d is the diameter of the indentation. Okay, next we got Rockwell test. Measures the depth of penetration instead of the diameter. The indenter is pressed onto the surface, first with a minor load, then with a major load. Difference in depth of the penetration is a measure of the hardness of a material. So in this Rockwell test, what happens is first the device is going to push down a bit with a really small load, and then not long after it's going to set its main load on the indenter. So for Rockwell tests we got 7 different Rockwell tests. We got Rockwell A, C, D, B, F, G, and E. For A, C, and D, we use the diamond cone, and for B, F, G, and E, we use a ball indenter. However, in BFG we use 1 per 16-inch diameter steel ball, and for E we use 1 per 8-inch diameter steel ball. So how do we calculate for the hardness number? Okay, so we got for 60 kilogram we got HRA, and then for 150 kilogram we got HRC, for 100 kilogram we got HRD, and so on. So what is this? We can acquire the hardness number by using this: 100 minus 500 times T. T is the difference in depth in here, as you can see, and this one. As previously mentioned, the Rockwell test measures difference in depth of the penetration. Next we have the Vickers test. So this Vickers test uses a pyramid-shaped diamond indenter and a load that ranges from 1 kilogram to 120 kilogram. The Vickers hardness number is indicated by HV, hardness Vickers. Impressions obtained are typically less than 0.5 mm in diagonal. So, Vickers test. For a Vickers test, we use a diamond pyramid, and this is what the indentation will look like. We get HV by using this formula. P for load and L is for the diagonal. Quite simple. And then we get the noob test. For this noob test we use a diamond indenter in the shape of an elongated pyramid. That looks like a pyramid that has been elongated in 2 of its corners, sorry. Applied load ranging from 25 grams to 5 kilograms. As you can see, this is a very small load. Noob hardness number indicated by HK. So, as I have previously mentioned, ranging from 25 grams to 5 kilograms, suitable for small or thin specimens due to being a micro hardness test, uses light load. So here is our new test. As I have previously explained, it uses a elongated pyramid. So the hardness number is calculated with this formula: P for load and L for its length in the indentation. Hardness testing procedures. So to do a hardness test, we have to go through a couple of procedures. First being, the zone of deformation under the indenter must be allowed to develop freely, meaning the indentation must be allowed to develop freely. Location of the indenter should at least be 2 diameters of the indenter from the edge of the specimen. So this is more of a minimum requirement. If we were to have a indenter located less than 2 diameters in the middle of the specimen, it would hinder the hardness testing procedure. Then next we have the thickness of the specimen should be at least 10 times the depth of the penetration of the indenter. Okay, the indentation should be sufficiently large to give a representative hardness value for the bulk material. So since we have so many indentation hardness tests with their own numbers and values, here is a scale that we can use to convert from one another. We got HB, HV, HRA, HRB, HRC, and so on. Next we have impact. So in this impact test, there are two main methods of doing it. First we got the ISOT test, and then we got the HRP test. So what's the difference? In this ISOT test, as seen here, the specimen is held up, standing up, with one of its sides held. Whereas in a HRP test, the specimen is laid down, with two of its sides held. Impact test. Impact toughness, energy from the amount of swing the pendulum, the energy dissipated in breaking the specimen can be obtained. So what happens here is, to start the experiment, this pendulum is to be set at a fixed height, and then it is let go, and as the pendulum travels down, it hits the specimen, and as it does, it loses energy, so it doesn't go back up to its original height. So we measure the value by looking for the difference in potential energy from this height, big H, and from this height, small h. Next we have metallography. The study of the physical structure and components of metals by using microscopy. Well, technically not every metals have to use microscopes, but I'll explain. Okay, so to prepare a metallographic specimen, first we need sectioning, mounting, grinding, polishing, and etching. First, sectioning. So I think this is best explained with an example. Say you wanna examine an engine block, the materials of an engine block. If you were to put a engine block under a microscope, that would be very difficult. So what you do is you cut a small specimen from the workpiece via a cutting tool, for example a big saw. Next we have mounting. So the specimen is mounted inside a resin for better handling, as shown here. This will make sense soon. Okay, next we are grinding. to even specimen surface and remove plastic deformation from sawing. A desirable surface is achieved by using successively finer abrasive particles to remove material from the sample surface. So we grind so that we can remove the plastic deformations from sawing. Why is there plastic deformation from sawing? So when you saw, you can actually see really small scratches, sawing lines, sawing deformations, sawing marks, and we hope to remove said marks by grinding. Desirable surface achieved by using successively finer abrasive material. So for this we start from the lower grits and we move our way up to the higher grits, more finer abrasive particles. Next is polishing. Not real technically, it's the same as grinding, but just to a really finer degree. And then next we got etching. So etching, in a nutshell, is basically grinding but with chemicals. So why do we etch? Structures the material grains on the surface according to their crystal orientation. Grain contrast etching. So etching, basically what it does is it removes the smaller imperfections in the material, and it exposes the crystals within the metal. Okay. And last but not least, we got analysis. After preparing the specimen, what we do next is we analyze. So there are really two types of analysis. First with the naked eye, and next with the help of a microscope. Material with sizable grains can be seen with the naked eye. This is called macroscopic techniques. Macro meaning big. And then for smaller materials, we use a microscope called microscopic techniques here. And without etching, these structures, these patterns would not appear under the microscope or with the naked eye. That's why we need to etch our specimen before viewing it. That's all I have to explain for today. Thank you and have a nice day.